Okay, so last class we finished your DC generators. So almost many things we covered in DC generator. So no need to repeat, because if we'll see the constructional features, they're almost equal for DC motor and DC generator. So no need to discuss more on this. And we'll focus which is very essentially required for the DC motor analysis, right? Just the performance analysis we do based on the terminal characteristics. In case of DC generator, the terminal characteristic is between the voltage and the current, right? Load current. And in case of motor, I told you in that class also, in case of motor, we have the terminal characteristic between the torque and speed. Okay. So then what is essentially requirement of this DC motor? Why we need DC motors? Because we are seeing everywhere AC, right? Here AC we have. Why essentially it is required that we should study about DC motor? Is it essentially required? So because DC motor, specifically it has two purposes. One is the speed control is very precise. We can achieve the speed control in case of DC motor precisely. Therefore, most of the servo applications, in control application, DC motor is being used instead of AC motors, like an induction motor, right, or synchronous motor. So, therefore, DC motors are also another advantage is the torque. In case of DC motor, we'll have high starting torque. It is much more than the AC motors. So therefore DC motors are preferred. We'll see how it is gradually, right? And in case of DC generator, we have seen there are varieties of generator, right? Similarly, we can also classify the DC motors. Like one is your self-excited, right, and separately excited. So, separately excited generator, if I'll say it has a value, right, it has some meaning. If I'll say separately excited motor, what it means? Because motor, the input to the motor is electrical energy, right? And again, if I'll say separately excited motor, what it means? That means I have to arrange a separate source for the field, and one source of course for the armature, and one more source for the field. So why I will not connect it to the same source, right? If I'll connect it to the separate source, then unnecessary burden, right? Unnecessary expenditure. So therefore, this separately excited motor is actually a vague term for the motors. It is not actually useful. Therefore, only we'll talk about self-excited DC motors, because separately excited motors doesn't exist in practice, DC motors. And we know that self-excited DC motors we can classify as shunt, series, and also compound, right? Okay. And of course we know there are classifications in compound motors, like we have cumulatively and differentially, right? Cumulative and differential compound motors. And of course, based on the connection of the field winding, we have short shunt and long shunt compound motors, right? So now we'll talk about this gradually about these motors. So before we move forward, let us see about the operational aspect. Already we discussed in the very beginning of your class how when a current carrying conductor, it is placed in a uniform magnetic field, how the torque will be developed. Okay, already we discussed this and will not talk much about that. It is based on the Lorentz force law, right? So this is a typical structure of the motor. Okay, now you can see there are two permanent magnets and one armature on the rotor. Armature coils are placed on the rotor, and these are the two brass contacts, right? And the field winding, of course, it can be permanent magnet or it can be excited by the same source where the armature is connected, right? Now, if, of course, the brushes are placed in the neutral plane, right? And here we can see that the torque will be developed based on the force developed on the current carrying conductors in the magnetic field, right? So therefore the torque will develop and it will start rotating, right? Okay. And the torque equation already we have derived in case of generator also. In generator we have derived the developed torque, that is Ka phi p Ia. The same will be applicable here in case of motor also, right? So this is Ka phi p Ia. What is Ka? K is the constant, which is nothing but what it is. Can anybody tell? K is Pz by 2 pi A. Right? Already we have seen this. And of course again we have seen the induced EMF. Generated EMF we can say, right? So generated EMF in case of generator is, it is because of the, when the coil is moving inside the magnetic field, this is the generated EMF. Now the question is, how this generated EMF comes into picture in case of motor? Why it comes into picture? Will there be, Of course there will be a generated EMF because the coil is moving inside the magnetic field and that will oppose its cause, right? So it will oppose the voltage applied to the terminal of the motor. Okay. So therefore this is, sometimes this is known as back EMF. In case of generator it is known as generated EMF, but in case of motor it is known as back EMF because it is opposing the main voltage which is applied to the motor. Okay. And if you write the terminal equation, now let me draw the equivalent circuit of the motor. If this is your motor, this is your field winding, right? Now one source is connected here, let us say Vs, okay? Because it is a motor, so it will draw the current, okay? And some load is connected to the motor. And this current IL will be equal to IA plus IF, right? So that means your IL will be equal to IA plus IF. Okay. So now, if I write the KVL, Kirchhoff's voltage law, obviously Vs will be equal to EA plus IARA. So of course the resistance will be here somewhere, that is Ra, right? That is the resistance of the armature circuit. So now your Kirchhoff's voltage law equation will be Vs equal to EA plus IARA. But in case of generator, what it is? In case of generator, the terminal voltage Vs or VL is equal to EA minus IARA, right? It is just the opposite, right? So now we can go ahead. So this will be, these are the equations related to the motor, right? Now the question is how we can start a DC motor. Can we start a DC motor like just supplying the connecting the supply? Will it work or it will start? You have seen it in the machines lab, right?
We have to do all the power. We have to do all the power.
Sorry?
We have to do all the power.
We have to
Do all the power.
spark. No, spark.
So we first get the field current, like first rotation of the field should be supplied to then the armature.
Okay. Rather than that also, field and armature they are connected together for a shunt machine, right? For series machine also they are connected together because we are not giving a separate source for the motor. We are providing same source, right? But why we cannot start directly just by turning on the switch? We need to put a resistance or we need to control the voltage across the armature. Why it is required? Because when the motor is about to start, the speed is 0, right? As the speed is 0, your back EMF will be 0. Okay? So as your back EMF will be 0, armature current will be Vs by Ra. Okay? And this resistance of armature is very small. Very small. It is in 0.2 or 0.3 range, right? If it is very small, then immediately if I will apply here 220 volt, let us say, and it is let us say 0.1 ohm, then it will become 2200 ampere. So as immediately 2200 ampere will flow in the armature circuit of the motor, then what will happen? It will burn, right? So your motor will be damaged completely. So therefore we should never start the motor by turning on the switch, particularly DC machines, DC motors, right? It will immediately burn your motor. And this precaution you should take in your lab very specifically. Don't start the motor just connecting it to the supply and turning on the switch. It will damage the whole motor, then you will have to pay the penalty. Okay? Maybe 20,000 rupees. Okay? So don't do this. Okay? So therefore, we never start a DC motor just by connecting the supply and switching it on. So we need to put the resistance. Gradually it will cut the resistance, and when the motor will achieve its speed, normal speed, then automatically the resistance will be cut, or it will be, we can say it will be away from the circuit, right? So now we can see in this circuit, here this is a permanent magnet DC motor where we have a rheostat here, variable rheostat, right? And this we can see it is gradually, it is shifting the contacts and it will connect finally and it will cut the whole resistance away from the circuit till the motor achieves the rated speed or the normal speed, right? So initially it will start with the full resistance, then it will gradually cut. Okay, you have seen how you move the rheostat, right? Rheostat you have to move, then it will cut the resistance and again it will connect not to its normal circuit, right? So this is how we start generally the DC motors. Okay, and it is very important therefore to put the rheostat in the armature circuit during starting, or we have a starter. You might have seen in your lab we have a starter with a handle. You have to move that handle gradually. So that means it is cutting the resistance gradually. Okay, full resistance to zero resistance, then it will come to the normal speed, right? So this is like a starter of the DC motor. Okay. Now we'll talk about armature reaction. So already you have studied the armature reaction for the generators. It is same except the change in the direction of the current. Because in case of generator, the armature provides the current to the load, right? But in case of motor, it draws the current from the source. That means the current direction changes. So if the current direction changes, what is the effect? the field generated due to the armature coil, that will be just reverse. There will be no other changes, right? Like we are putting the interpoles and compensating windings, that will remain as it is. We need not to change it because they both are connected in series with the armature circuit, right? The interpoles and the compensating windings we have studied earlier also. The two things we need for the compensation of armature reaction. One is your interpole, right? And other one is your compensating windings, right? So these connections of the interpoles and compensating windings need not to be changed because they are connected in series with the armature. Whatever direction the current will flow, accordingly in the interpoles and the compensating windings it will adjust and it will oppose the field generated due to the armature, right? So therefore no need to change the connections of these interpoles and compensating windings. Rather rest will be fine. So the armature reaction, whatever arrangement to counteract the armature reaction in case of a generator, same generator exactly can be used for the motoring action as well, just by changing the supply, right? So we'll get the motoring action as well, right? Okay, like we have seen in case of generator, one term that is known as voltage regulation, right? What is voltage regulation? Voltage regulation is V no load minus V full load by V full load into 100, right? It is in percentage. So this voltage quantity is the terminal quantity by which we check the performance of the generator, right? Similarly, for the motor we need a terminal parameter by which we can check the performance of the motor. Of course, efficiency is one parameter to check the performance for the motor as well as generator. But except the efficiency, there are two other parameters. In case of generator, we call it voltage regulation because voltage is the terminal parameter for the generator. And in case of motor, it is the speed. Speed is the terminal parameter of the motor. So therefore, in case of motor, it is the speed regulation. And in the same way, it is defined as no load speed. That means when there is no load on the motor, what is the speed? Minus when the motor is fully loaded divided by the speed under full load into 100. And same thing we can write in RPM and radian per second. So these are in the radian per second, these are in revolution per minute, right? So therefore, this is your speed regulation, and this is the important parameter for checking the performance of the motors. Okay. Speed regulation, we'll see, speed regulation of a shunt motor is almost negligible. But in case of speed regulation of the series motor is very high. Okay. So therefore, for different application where the speed regulation requirement is very high, we need to use the series motor, and where the speed regulation is negligible, we can use the shunt motors. Okay. Now I'll talk about the losses in the DC motor. Already we have seen this in case of DC generator, right? So in case of DC generator, what are the losses? We categorized into, what are the losses we have studied? One is your electrical loss, other one is your mechanical loss, right? So mechanical loss plus magnetic loss, you can say. Okay? So this we represented through PR, right? And this electrical loss is your copper loss, or we wrote it as PCU generally, right? Copper loss. Okay? So now, similarly in case of DC motor also, the losses take place, same kind of losses, only the power flow is in a different direction. Like previously the power flows from mechanical domain to the electrical domain in case of generator, but here in case of motor the power flows from electrical domain to the mechanical domain, right? That is the only difference. Now we can see here in this diagram that how the power flows. This is your electrical domain, P in equal to VSIL, that is the input power, right? And as soon as we give the power, the current starts flowing in the circuits, armature, then field, right? Then of course we have copper loss, okay? And if we'll take out the copper loss, we'll have developed power, that is EAIA, and that is equal to TD omega M, right? Okay, that is the developed power in the armature. Now from the developed power, if I'll subtract this this rotational loss, that is consisting of frictional loss plus magnetic loss, if I'll subtract it out, I'll get the actually output power, that is called shaft power. That means the power we take from the shaft is known as the shaft power or output power, okay? Okay, so this is how the power flow in case of DC motor, right? Now we'll talk about different kinds of motor, like we also talked about different varieties of generators. So here we'll talk about different varieties of motors. So first of all, we'll talk about the series motor. So what is a series motor? Series motor means, of course, as the name suggests, the field winding of the motor will be connected in series with the armature, right? Armature winding. Like we can see here, we have a motor here, right? And this resistance is your armature resistance, and this is your field winding, where the Ns is the number of turns in the field winding, and Rs is the resistance of the field winding, series field winding, right? Of course, we have a starter circuit. We cannot neglect starter, whether it is a series or shunt or compound motor. We have to put a starter all the time, right? So therefore, this is your starter. Okay. And now you are connecting a voltage source Vs, and this is your series motor, right? Now if I write the equations for this, now the field flux phi p, I can write it as KFIA, because the same current is flowing through armature and the field. Therefore I can write KFIA. Kf is the proportionality constant, right? And then it will lead to the induced EMF, which will be equal to KFIA omega m. Instead of phi p, I can write KFIA, right? Okay. Then I can write the developed torque in case of this series motor will be KFIA square, because just TD equal to what is K phi p IA, right? Just substituting phi p equal to KFIA, it will become KFIA square, right? So therefore, what we observe here is that this developed torque is directly proportional to Ia square. So this is the best quality of the series motor. It will produce a very high starting torque, because in the starting the current is very high, right, as compared to the no load or full load operation, right? So when we need a high starting torque, therefore most of the time in case of tracking motors, this series motor is preferred, series DC motor is preferred, right? So we can generate a high starting torque because of this equation, right? TD is directly proportional to Ia square, right? And similarly, other terminal equations we can write by applying the Kirchhoff's voltage law. So I can write EA equal to Vs minus Ia, Ra plus Rs plus Rax. Rax is the resistance in the starter circuit, right? So net resistance, if I'll represent as R, then I can write Vs minus IAR, right? So then omega m is equal to, from this equation, I can write omega m equal to Vs minus, because we know Ea equal to omega m K Kf Ia. So by substituting this instead of Ef, so if I'll substitute this in Ea here, then by segregating omega m, I'll find Vs minus IAR minus K Kf Ia, right? Okay. So now this is the equation for the speed. Now we want to find the characteristic of the terminal characteristic, right? That is speed versus or torque versus speed, right? Okay, so let us see how we can do this. So this is your characteristic. So how this characteristic is achieved? This characteristic is between the speed and the armature current, and torque and the armature current, and the PD and the armature current. So here first if we'll see the speed versus armature current, so if we'll see this equation, right? So from this equation we can draw this kind of characteristic because it is inversely proportional, right? So therefore your characteristic will become like this, omega versus armature current. Okay. If I will now take torque, developed torque versus armature current, because it is proportional to the square of armature current, so it will become a exponential increasing current, right? So you can say like this, it is I squared torque, right? Similarly PD, what is PD? PD is equal to Ea omega m, right? Or else I can write it as, it is Ea Ia, okay? Ea Ia or TD omega m. So from this equation I can find this type of characteristic, right? Okay. Okay, so now we'll see the characteristic of the torque versus speed. Okay. So here you can see the torque equation already we have derived. So the torque equation is TD equal to Ka Kf Ia square, and we know Ia equal to this from the terminal equation, right? Ia equal to Vs minus, so Vs by K Kf omega plus R. If I'll substitute this here in this equation, right? So I'll get this equation. That is K Kf Va square by R plus K Kf omega m whole square, right? So this is your TD. So now from this equation I can draw TD versus omega m, right? The characteristic. And again for PD I can write this equation, that is if I want to draw PD versus omega m, then I need to find PD in terms of omega m, right? So PD I know Ea Ia, so substituting Ea as Vs minus IAR into Ia, so I will get this equation, right? Then I need to find the maximum point where the maximum of PD will occur. How I will find? Just by taking the derivative of PD. If I will take the derivative of PD with respect to Ia and substitute equating to 0, I will find the current where the maximum value of PD will occur. And after derivating and equating to 0, I found this IAM is equal to Vs by 2R. So now if I will substitute this IAM in this equation, in PD equation, I will get PD max, right? PDM, that is maximum developed power produced. So I will find this PDM will be Va squared by 4R. This you can check it, you will find the same thing, right? Now I can draw the characteristic of TD versus omega m and PD versus omega m. So if I, of course, if I plot TD versus omega m, it will look like this because it is a inverse characteristic, inverse square, right? And PD characteristic will be like this, having a peak value where this peak is equal to VA square by 4R. Okay. So these are the characteristics of the series motor. We studied the characteristic of omega m versus IA in the earlier slide, right? And TD versus IA, and PD versus IA, right? And here in this characteristic, it is torque versus speed, right? And your PD versus speed, right? Okay. So these are the characteristics of the series motor. Now I'll talk about the shunt motor. Okay, it is the similar structure as of the shunt generator, right? So this is the structure of the shunt motor. Generally in the electrical machines lab also you connect like this, like the armature circuit is here and it is connected through the starter, right? Starter resistance, and then the field is connected in parallel. Because we need to connect the field in full, we should not reduce the field current because field coil resistance is very high. So we should not reduce the field current, right? So therefore the starter, we can see here, starter is connected only in series with the armature circuit, right? It is not in series with the field winding, right? Field winding is directly connected to the source. Here we can see, right? Okay. So now it is very clear. Now you can write the equations, the terminal equations for torque and power, right? So torque equation already we know, this is your torque equation. If there is no variable resistance here in the field, then your phi p will be constant, right? Because it is connected to a constant voltage source. So your phi p will remain constant. So therefore TD will become equal to KIA. So your K phi p will be equal to K. It will become constant. So now it will be equal to KIA, right? Now we need to write the equations of the torque and the power versus the armature current. So developed torque equation is this, KIA. So it is a very simple equation. It is a straight line, of course, right? So actually it should be straight line, but because of the armature reaction, presence of the armature reaction, if it is not properly counteracted, then it will somehow have a curved structure in the full load condition, right? Because under full load the armature current will increase and that will lead to armature reaction, which will cause the torque in decrease. As the armature current will decrease, the torque will also decrease, right? So therefore a little nonlinearity will exist during the full load condition if the armature reaction is not counteracted properly, right? So this is the equation for KIA. Okay, and when we actually consider the armature reaction, then it will become a little bit nonlinear structure, right? Okay, now we'll talk about the terminal equations. Your EA will be equal to Vs minus IARA, and your omega m will become equal to, of course we have derived this, Vs minus IARA by K phi p, right? And from this equation I can write omega m is equal to omega m NL, this is your no load speed, minus RA by K phi pi. Can I write this? Because how can I write this? Just little bit manipulating this, I can write this. Omega m equal to Vs by K phi p minus Ra by Ka phi p into Ia, right? Now Vs by Ka phi p is nothing but it is equal to the no load speed. Why it is no load speed? We know that omega m is equal to Ea minus, sorry, it will be Vs minus Ia Ra by K phi, right? So now under no load condition this Ra is equal to almost 0. Almost is it negligible because it will supply only the no load losses, right? So it is negligible, therefore we can consider as 0. So therefore under no load condition, so your no load speed will become Vs by K phi p. So instead of Vs K phi p, I can write omega m NL, that is speed under no load condition, right? So therefore your omega m is equal to omega m NL minus Ra by K phi p into I. So omega NL here is a constant, right? Okay. So now we can see this is your speed, okay. Now if I plot the speed versus armature current, how it will look like, because we know this armature resistance is very small, okay. So as this Ra is very small as compared to your K and phi p, so the drop will be very negligible here. So therefore the speed will remain almost constant as your current will increase. As your load will increase, your current will increase, the drop will be very minimal. Therefore from the characteristic you can see as the current is increasing, the drop is there but it is not very high. It is very small, right? Okay. So therefore in case of shunt motor, the speed regulation remains almost constant. Okay. Speed regulation remains constant in case of shunt motor. Okay. It is prominent from this characteristic, right? So
Sir, the C curve is wrong, right?
it is not wrong. It is actually when we can say that it is based on the compounding, right? Over compound or under compound. It is not like it is for the same like shunt motor when it is in the compound structure. It is a level. The C curve is for the compound structure, okay, not for the shunt motor. Okay. So this TD, now the developed torque will be equal to K phi p Ia, and that is equal to KIA, right? So already we know this. Now omega m is equal to Vs minus Ia Ra by K phi p, okay. And from these two equations, I can derive this, that is torque versus speed, okay. Just by substituting speed in case of torque equation, from this equation I can segregate current Ia, and if I'll substitute here in this equation, torque equation, I'll find torque is equal to K phi p Vs by Ra minus K square. This will become square, right? Phi p square, okay. It will be phi p square by Ra omega m, okay. So now we can plot this torque versus speed, right? So if I'll plot this, it will look like this. This is your torque versus speed curve. It will be a straight line with a slope as from this equation. This is your square, right? Square term. So this quantity is very huge, therefore, and when the omega m is equal to the no load speed, so it will become, the torque developed will become 0, right? Okay, so similarly PD, from this PD equation also we can draw with the maximum value, where this maximum value will be this, right? At this current we'll get the maximum value of the developed power, and the maximum value of the developed power will be Va square by 4 Ra, like we have derived in case of series motor, right? So both for series and shunt motor we have seen the characteristic and the performance. So we'll stop here, maybe we'll continue tomorrow the compound motors, right? Okay, so thank you very much.